We are back with fluorescence spectroscopy again. So, we are close, very close to the concluding part of this course, only maybe few lectures are left. So, at this point we are going to get you, I am going to get you a brief overview, not exactly everything in detail because of the limitation of time or limitation of lecture numbers. So, I am just going to get you some overview of a topic which is very relevant, very fascinating nowadays, that is related to materials. Because when we talk about fluorescence, okay, when we talk about fluorescence is a technique that is used by chemists, used by physicists, used by biologists for their different studies involving molecular system or maybe involving systems which fluoresce. And fluorescence is a very sensitive technique, as I discussed in some earlier lectures, that it is very sensitive and many properties, I mean many properties of the molecule is getting affected, like maybe photophysical properties or and so on. So, as a result of different perturbations, and we can look into those perturbations. Okay. So, so today basically we are just going to have some overview of what is fluorescence, its connection with photoluminescence, and ultimately what are these photoluminescent materials and how these materials are prepared. It is not exactly like we are going to have a detailed discussion on this, but an overview or maybe some representative examples which will get you some idea of fluorescence spectroscopy or maybe photoluminescence spectroscopy in the domain of materials, because materials means wherever you go, wherever you look into, you will be finding different materials. Okay. Starting from maybe everyday usable material or maybe drugs, etc., that is these capsules, etc., maybe many other things, okay, where you find a tremendous application of these material. These materials maybe in some cases these are naturally available, or maybe it is synthetic materials. Okay. So, when we are in materials domain, so that is why since this era is the era of materials and also era of bioscience, therefore it is very pertinent to talk a little about maybe about these materials and its connection with luminescence spectroscopy. Okay. So, so basically we are going to concentrate a little bit on nanomaterials and their applications. Not basically I am going to talk about applications, just I shall give you some ideas, means how these nanomaterials can be applied, and during application, okay, during the application of these nanomaterials, how spectroscopy can help us. It may be extinction spectroscopy, it may be luminescence spectroscopy, it may be photoluminescence spectroscopy. Okay. So, nanomaterials are basically whenever we talk about nanomaterials, it is nanoparticles, and another term which is coming, it is your quantum dots, and these are having fascinating fascinating chemistry, fascinating fascinating properties. Okay. So, just some overview I am just going to present to you. Okay. Now, as this course is basically related to fluorescence, or in broader sense luminescence. So, let us have some idea of various types of luminescence. So, the term luminescence starts, then it has photoluminescence, that is photon emission, okay, and it may be phosphorescence, it may be fluorescence. And phosphorescence and fluorescence, what is phosphorescence, what is fluorescence, I already have discussed in some earlier lecture. It may be another type of thing, it may be electroluminescence, okay, electrically generated, then triboluminescence, then crystalloluminescence, then sonoluminescence, then chemiluminescence or bioluminescence. Okay, these two things I already gave you some idea. Okay, then radioluminescence, scintillation, and then thermoluminescence. These are the different types of luminescence, and of which photoluminescence is the concern of is our concern mainly, because it is related to fluorescence spectroscopy. Ultimately, it is related to fluorescence spectroscopy. And fluorescence and phosphorescence, as you know, that these are the two two phenomena, and it is light emitting phenomena, and it is segregated in terms of their time scales, okay, and also depending on the spin parentage of the system, I mean whether it is spin forbidden process, or maybe it is spin allowed singlet to singlet or triplet to triplet process. Based on that, it may be called as phosphorescence or fluorescence respectively. Okay. And fluorescence is commonly used when the energy source is ultraviolet visible light, and photoluminescence is commonly used when the energy source is an electromagnetic radiation. Okay, and this electromagnetic radiation could be gamma rays, could be X-ray, could be ultraviolet visible. So, it is a visible light. So, it is more a general term. It is more a general term. Okay. So, that is why in case of materials, in most of the cases this term is commonly encountered, I mean commonly used is this photoluminescence. It is a general term because in case of materials you may have fluorescence, you may have phosphorescence depending on the phenomenon you are looking at, but the thing is this general term is used. Okay. Now, so we are at this photoluminescence, and photoluminescence means you would like to measure, what you would like to measure? You would like to measure this intensity as a function, intensity of emitted or intensity of luminescent radiation as a function of wavelength. Maybe you can measure intensity at different excitations. Okay, maybe you measure the lifetime of a particular emission at a particular wavelength that you can measure. So, these are the various aspects naturally come into action when you start with this photoluminescence of different materials. Photoluminescence of various materials means here we are mainly concerned about this nanomaterials or maybe quantum dot. So before going into what is quantum dot, what is quantum dot, or what is I mean how nanomaterials are prepared, or these things should be means we should get a better overview of how these materials are prepared. So, we will start with the general thing, nanomaterials, and then maybe at some other point of time, maybe in another lecture, we will talk a little more about this quantum dots. Okay. So, let us step into it one by one. Okay. So, before going into it, we should get familiar with the term nanotechnology. So, what is nanotechnology? Because it's a technology. Okay, that is, nanotechnology is the understanding and control of matter at dimensions of roughly 1 to 100 nanometers. That is why the term nano is coming. Okay, nano is coming, nanometer, where unique phenomena enable novel applications. So, some novel applications are expected, okay, and of which we may be concentrating a little more on on the fluorescence or maybe photoluminescent aspects, okay, or the aspects which are related to this fluorescence spectroscopy. Nevertheless, other things are also important. Maybe we'll talk very little about those if time permits. Okay. At the nanoscale, the physical, chemical and biological properties of materials differ in fundamental and valuable ways from the properties of individual atoms and molecules or bulk matter. So these materials are different from single atom or maybe segregated atoms or maybe distributed atoms distributed in various regions of your container, okay, or maybe molecules. It differs from individual atom or molecule, okay, and also it differs from the bulk material. Like suppose you have a silver rod, okay, suppose you have a silver rod, suppose you have silver atom, okay, and you have in between like silver nanomaterial, okay. So by this term it is different means their properties are different, their behavior is different, okay. So that is the main point of understanding in this nanomaterials nanomaterial world. Okay, so nanotechnology research and development is directed towards understanding and creating improved materials. Okay, suppose you have a material, okay, and maybe that material is not serving your purposes. So therefore, what you want to have, you should use some technology, you should invent some technology by which you are generating some better material which can be applied for some other applications, maybe some devices, maybe some systems. That is and how to use that. We would have to use those fascinating properties, those properties which differ from atom molecules to and also with this this bulk material. Okay, so that that means you are at the interface of this atom molecules and also this bulk material. So you are in between. Okay, and since these properties are their properties, these nanomaterials have fascinating properties. So maybe why not exploiting those properties in some applicative reasons. Okay, so let us look into the scale of things in nanometer. Because it is nanomaterials and quantum dots. Okay, so let's look at here. See here, it is 1 centimeter, 10 millimeter. So it is in meter scale. Okay, it is in meter scale. Then it is in micro scale. Okay, like 100 micrometer. Okay, like 10 micrometer, like 1 micrometer. Okay, and of course automatically this color is changing and also the band is differing. Like here it is microwave, this is infrared, this is visible, this is ultraviolet and so on. So practically here it is the nano world, this is your micro world. Okay, so particles having diameter, okay, of the order of 10 to 100 nanometer. 10 to 100 nanometer means these are called as in general nanoparticles. So nanomaterials with these dimensions are nanoparticles, and 1 to 10 nanometer these are nanocrystal, and this in this domain of nanocrystal quantum dot is residing. Okay, so quantum dot will come in this region. Okay, so I will come to quantum dot later on, but let us have some overview of what are these materials and how these are prepared, and then what applications we can have and what applications pertinent to fluorescence spectroscopy can be there. Okay, so we will have some applications, we will just discuss some application. Okay. So, this is the scale of things. So, therefore, we are in this region. We are talking about materials whose dimension is falling in this region. Okay. Okay. Now, next question automatically comes is that how to synthesize these materials, okay, because it is the question of getting newer materials. So, question is you have to synthesize this material. So, there are two different ways of synthesizing this material. One is your top down and the other one is bottom up. Okay. So, top down one is you have a bigger material like this. So, you have a bigger material and then you are cutting it into pieces. So, half, then next half, 1/4, then 1/8. This way you are keeping on reducing the length of this cut. Okay. And ultimately you may achieve dimension of the order of like several nanometer, like maybe 10 to 1000 nanometer. Okay. So, this is the basic idea of this top down approaches, that is you are progressively cutting into pieces. Okay. And it is basically ball milling approach one is called, another is thermal cycles. Okay. So, it has got thermal cycles, then particle distribution is of the order of this 10 to 1000. You see that 10 to 1000 nanometer is a broad, very broad distribution, but still you can get nanomaterials. Okay. So, and the point is that it depends on how you are cutting this into pieces. Okay. And every time this cutting may not be reproducible. So, if every time the cutting is not reproducible, then the problem comes with the reproducibility, and also this distribution pattern. Distribution pattern is is becoming very broad, as a result of which it is coming out to be 10 to 1000 in this range. And of course, naturally, since there is a wider size distribution, therefore this particle shape or geometry, individual particle which you are generating, the shape and or geometry is different. So, you cannot get this reproducible geometry every time. Okay. Impurities are also matters of concern. So, for nano composites and nano grain bulk materials, so they have lower sintering temperature, for lower formation temperature. So, therefore, the approach which is your top down is basically you are making, suppose you have a larger some material, say maybe material which is a piece of metal, and then you just do the grinding. Therefore, you will be getting the powder. Okay. And again, if you do more grinding, okay, on this powdered material, then you may be getting still smaller size. But the problem is that it is your size distribution may not be even. It is a broad size distribution. On the other hand, the opposite approach. So, in this case, you have bigger things, then you make it smaller, then still smaller, then still smaller, then very small. Okay. This way you are doing. Okay. But in other case, so it is top then down. Another one is you have smaller, then bigger, like this. So, it is bottom up, that is your starting material or starting thing is very small, and from which depending on your necessity you can maybe go you can go up to this or maybe go up to this. So, in this case maybe size control it may be possible, but in that case you need to have a control over the process. Okay. So, two approaches are there. So, one is thermodynamic equilibrium approach. Okay. One is the generation of supersaturation, then nucleation, then subsequent growth. So, these are the three things that is important. So, therefore, it is first approach is thermodynamic equilibrium approach, and the second approach is kinetic approach. It is by limiting the amount of precursors for the growth. Okay. So, thing is that if you do not supply too much of precursor, then your suppose you do not supply too much of this. So, therefore, what will happen, the process will stop at some point, and therefore, and depending on the kinetics of the process, ultimately maybe the one which is kinetically controlled, maybe that will form to a larger extent, and therefore, and of course, you have to confine the material in some limited space. So, therefore, thermodynamic equilibrium approach means it is the one which is thermodynamically more stable, that you are talking about, and for kinetic one, the one which is kinetically formed at a faster rate, So, this way you can do the bottom up approach. Okay. So, top down is here, bottom up is here. So, you have this thermodynamic equilibrium, and the other one is kinetic, Okay. So, these are the different approaches for nanomaterial synthesis, and the point is that this for nanomaterial, so this is basically the overview. Okay. Let us see. So, different methods for nanomaterial synthesis. This may be chemical method. You can find out many literatures regarding this chemical method. Then another is photochemical method. Okay. Then the third one is electrochemical method. Fourth one is sonochemical method by using this sonication technique. It is called the sonication technique. The other one is laser ablation technique. Okay. And the other one is also this microwave irradiation technique. So, there are several methods for the synthesis of nanomaterials. Okay, several methods like this, and you can still find other methods as well. These are the broad overview of the different methods. Okay, so maybe if you look into a specific method, then you will be finding different subdivision under this specific say photochemical method. Okay. Okay, so this is also this also gives you the overview of different, I mean not exactly in detail, but for just knowledge purpose, you can get this idea of what are the general methods for synthesizing these nanomaterials. Okay. Now, regarding photochemical method, as I told you, it is important advantages of photochemical method is that basically when you want to synthesize this nanomaterial, suppose nanomaterial means it is uncharged system, materials do not have any charge. So, suppose you start with some ion Mn plus, then you reduce, so you generate M, okay, and then this M will ultimately cluster with each other. So, M plus M, that gives you this way M2, then and so on, and this way you will generate like this small nanoparticle, and depending on whether it is a thermodynamic equilibrium process or kinetic process, your size, I mean the particle size will also vary. So, the reduction of metal ions in this case for photochemical process, okay. So, reduction of metal ions can be controlled easily by slow in situ release of reducing agent using photons or lights. That means photons can be used as light catalyst for the process, that is you can control, okay. And excess reducing agent may not be essential. Photoreaction is highly specific and reproducible. As for example, just I am giving you the since we are very close to photochemistry in the sense that we do, I mean here we discuss this fluorescence spectroscopy, that is why I picked up this photochemical method in general to have a little more overview. Okay. Okay, let us see. So, photochemical route for the synthesis of metal nanomaterials, like as there are several methods available, of which I am just giving you an idea. Preparation of polymer stabilized colloidal silver by ultraviolet irradiation technique. In this case, methoxypolyethylene glycol generates free radical in presence of UV radiation and acts as reducing agent towards the silver ion. So, therefore, silver ion is reduced, and also in the one important point is that when you generate this nanomaterial, okay, like this clustering of small particles, then you need to have something outside as a coating, so that this agglomerate is stabilized. Okay. So, that is why here this methoxypolyethylene glycol is acting not only as the free radical generator, which is ultimately reducing the silver, and as also it serves as the stabilizer for the silver nanoparticles which are generated. Okay. So, this is one method. Another method could be photochemistry of involving the photochemistry of aromatic ketones to Norris type 1 cleavage of benzoins via photoreduction generates ketyl radical that readily reduce many metal ions such as for example silver and gold. So, this can be another method. Okay. And the third one is as we are more concerned with this luminescent materials. So, highly luminescent, that is why I picked up this example, that highly luminescent silver nanoparticles AgFNP, silver nanoparticles which is fluorescent, these have been prepared by facile photochemical method yielding these materials in just a few minutes. So, it is not taking long time, and with excellent long term stability. So, stability is also important, because we are talking about the about a material, we should be getting a material which should be stable for a fairly long time. If it is not, then you know the effort may be of not that importance, because of the fact, suppose that you synthesize one material which is not very stable, but you want to apply that material at some distant place where you need to transport that material. So, during transportation, if the material is lost or if the material is damaged, then you may not be able to use it. So, that is why a long term stability is important factor in this materials chemistry. Okay. And in this case again this ketyl radical, as I told you over here, that reduces silver ion from silver tetrafluoroacetate in presence of amines, and thereby generating this fluorescent silver nanoparticles. So, when it is fluorescent, then it is of more interest to us, because maybe we can utilize that fluorescence behavior in some applications, maybe in some applicative reason we will be employing it. Okay. Okay, then but the point is, since we are discussing a little bit detail about this photochemical method, so eco-friendly methods are very important. Eco-friendly approach for the synthesis of nanomaterials is very challenging, and it is very wanting. Okay. So, due to their wide range of applications, there means these nanomaterials wide range of applications, especially involving human contact, as for example glucose sensing, maybe amino acid sensing, biomolecule sensing, water soluble ion sensing, and biological imaging process. So, therefore, if you maybe in most of the cases these materials will be in contact with human system or maybe living system. So, therefore, if your material is if it is a toxic, then it will be a problem. So, not only it has to be fluorescent, but at the same time if it is less toxic, then it will be more interesting to us. So, therefore, there is a growing tendency to develop this eco-friendly processes for the synthesis of nanomaterials without using any toxic chemical or without using that much toxic chemical. So, that is very wanting. Okay. Because here we are mostly interested in applying this nanomaterial fluorescence or nanomaterial luminescence, photoluminescence for various applicative reasons. Okay. So, now nanomaterial based, as I told you, that what could be the possible applications of such a nanomaterial. So, it will be nanomaterial based sensing of several ions, like maybe toxic ions such as sulfides, cyanides, it is deadly poisonous, this cyanide. Lead is also toxic, cadmium, it is a heavy metal, then mercury is also heavy. So these are toxic metals, okay, and these are found to be widely distributed in both environment and in living systems. So maybe if its concentration, I mean if the concentration of these ions, okay, in living system it is more than the limiting concentration, then it will be toxic. So therefore detection and estimation, okay, this is very important, okay. And these nanomaterials have some fascinating properties that you can exploit those property in selectively identifying these ions, and we will be coming to those points after after a little while, okay. So what are the possible techniques? I mean nanomaterial based sensing, okay. So possible techniques could be colorimetric UV visible spectroscopic technique. So it is again a spectroscopic technique, okay. That means you measure the color, or you may measure you may measure this absorbance maxima and also the absorbance at some wavelength, and using that maybe you can estimate your material. Material means your estimate your this ions, okay. Another is photoluminescence quenching. This is another thing. We'll be discussing this particular issue maybe in later part of the next lecture, okay. But this is another thing, I mean where this photoluminescence quenching, okay, I mean nanoparticle photoluminescence quenching will be used to do sensing things, okay. Another is fluorescence turn on assay. These are catchy terminology, but these are also interesting, okay. That in this case your fluorescence may be suppose due to something the fluorescence was quenched. Now if you add some ion, then maybe due to some interaction the cause of this quenching of fluorescence is lost, and as a result of which this fluorescence is again turned on. So quenching is lost, and therefore fluorescence is again obtained back, and this is called fluorescence turn on. And this may be there are plenty of examples you will be finding in literature, and maybe I will be citing some of them, or maybe at least one of them, to show you that maybe selectively adding some ions, okay, you can selectively do this turn on assay, okay. So therefore we are slowly coming to the point that in nanomaterial based sensing of ions you can use this photoluminescence quenching or maybe fluorescence turn on assay. In addition to that, you can use this colorimetric as also this UV visible spectroscopic techniques, okay. There is one example where synthesis and characterization, I mean it is a simple synthesis of CTAB stabilized, because as I told you that you need to have stabilizer, okay. Otherwise in most of the cases your nanoparticle will not be stable, because in order to keep those nanoparticles which you are synthesizing, okay, in order to keep those nanoparticles in solution, you need to have a means to make them solubilized. So this solubilization process is done by the stabilizer, and here in this particular example it is the below CMC CTAB, cetyl trimethyl ammonium bromide stabilized silver nanoparticle, okay. And this is done by a very simple and elegant method, as I have discussed in some other lecture about this this azo food dye, okay, and this azo food dye interaction with this serum proteins, okay. In this case this azo food dye has got a newer dimension, that it can be used to do the reduction, okay. So photochemical reduction of silver ion to silver nanoparticle. Okay, in the same way what is happening, that because of this photochemical reaction this dye is degraded. So, it is nothing but a but the environmental remediation as well. Okay. So, in addition to the formation of nanoparticle, this dye is also degraded. So, you have got this dye, then silver nitrate and sub CMC CTAB you add, and then you irradiate with visible photon, you generate this nanoparticle. Okay. This is the color of the nanoparticle, this is the nanoparticle plasmon band. What is plasmon, I will come. So, this is the characteristic band for silver nanoparticles, okay, and this diameter is of the order of 10 to 12 nanometer diameter. Okay. So, it is a little bigger than this nanocrystal dimension, but this nanoparticle has got some fascinating sensing applications. Okay. Some fascinating sensing application. Before that I must emphasize that this method is this method of synthesis of this sub CMC CTAB stabilized silver nanoparticle is indeed an eco-friendly approach. Eco-friendly approach means under eco-friendly condition you are doing this, because you are using very little concentration of CTAB, because high CTAB concentration may be problematic, and also you are not using any toxic chemical, because these dyes are toxic but not that much toxic. Okay, because these dyes we generally take with colored food. Okay, therefore, it is toxic, it is not good for health, but still it is less toxic than other toxic chemicals which are used as reductant of this silver nitrate. So, therefore, that is why it is called under eco-friendly condition. Okay. So, now let us look at the possible application of this. Possible application means this nanoparticle is generated. Okay. So, nanoparticle is generated, and then this nanoparticle is how this can be used up for some applicative thing. Okay. So, let us move on to the next slide. Let us see what is there. Okay. So, one is, as I told you, that here this sensing technique. So, it may be colorimetric visible spectroscopy technique or maybe fluorescence technique. So, let us first have a look at what is happening in sensing application, what is exactly happening. Okay. So, in this case what is happening, that it is used for these nanomaterials are used for the selective detection of water soluble sulfides and cyanides. So, these are this is deadly poisonous, and this is also very toxic. Okay. So, what is happening, that as you keep on adding this more and more these ions, you see that this is the characteristic band of this nanoparticle in absence of any cyanide or in absence of any sulfide. So, when you increase the concentration of added sulfide or cyanide, you see that this band is decreasing, and you see if you look into these test tubes, okay, containing nanoparticle plus different concentration, different concentration of sulfide, you see that this color is fading along this. You see that it is more yellow, it is less, and it is about 60 micromolar. It is very similar to water, as if there is no color. So, color is completely lost, there is nothing in this region. Okay. This also happened in case of when cyanide is added, you see that similar trend is there. Okay. And this is because of the fact that this nanoparticle is etched as a result of this one. Okay. So, particle is becoming smaller and smaller, as a result of which this characteristic plasmon band for the nanoparticle is lost, and therefore we can see it. Okay. So, simple UV visible technique, simple spectroscopic technique can be used, okay, can be employed along with your nanoparticle in sensing, okay, in sensing, or in identifying different ions. Okay. Now, the point is that this particular study was also tested with other ions, or maybe this is done, this was done in presence of other ions, but the thing is that in presence of other ions the sensitivity of the process is unchanged, plus no other ion is having any capability of doing this type of color fading. Only sulfide and cyanide, these are found to be very efficient in bleaching this color. So, from this color change you can in principle, you can in practice detect this water soluble ions. Okay. Next question is that if we can have a fluorescent tag that may attach with your nanoparticle, maybe in some non-chemical way, that means there is no true bond formation, but there may be some attachment with this nanoparticle. Suppose you have some fluorescent molecule which attaches onto the surface of the nanoparticle, okay, and then you can follow this process as a function of this fluorescence behavior of that attached molecule. Okay. So, let us look into it, how this can be done. Okay. So, this is called your fluorescence turn on assay. So, this is a true application of nanomaterial in sensing different ions. Okay. So, fluorescence turn on assay is that you have, suppose you have coumarin 314 molecule, it is a dye molecule, it has strong fluorescence, okay, and the structure of this molecule is this coumarin 314, okay, it has got a very strong fluorescence. Now, the point is, the moment you add your nanoparticle, that is sub-Sims stabilized nanoparticle, what is happening? That its fluorescence is, okay, its fluorescence is lost, okay, because of the fact that this particular molecule is getting attached with this nanoparticle, these nanoparticle, this one, okay. Therefore, this fluorescence is turned off. So, the fluorescence of this molecule is turned off because of the interaction of this with the nanoparticle, okay. And then to this, if you add, okay, if you add this Q+ ion and then sulfide, okay, then what is happening, that these ions are, this C314 is released, and therefore fluorescence is restored, okay, fluorescence is restored, okay. But on the other hand, in presence of lead, okay, in presence of lead, if you add this cyanide, then what is happening, that the same thing is happening, that your fluorescence which was initially quenched is now turned on. You see that it is just a white type of light you are seeing with very little fluorescence, due to this coumarin 314. That means most of the coumarin 314 fluorescence is quenched as a result of this interaction of this nanoparticle, nano silver, with this coumarin 314. Okay. Now, when you add this sulfide, why in presence of Q+? Because the point is that since this particular nanoparticle is sensitive to sulfide and cyanide, so selectively you can do this turn on in presence of Cu2 Cu+, so that in that case only the sulfide, okay, will interact with your nanoparticle and thereby releasing this C314. Okay. In other case, in presence of Pb2+, if you add Cn-, then it etches this nanoparticle, original nanoparticle containing this C314. So, since this particle size is is reducing as a result of etching. So, therefore, some of this C314 molecule is getting dislodged from this initially attached stage, and as a result of which this free C314 is going to get you this this fluorescence turn on. So, what is other reaction is that in presence of cyanide it is forming AgCN2, in presence of sulfide it is forming Ag2S precipitate. Okay. So, therefore, this silver, a portion of silver is taken by these sulfide or maybe by this cyanide, and as a result of which its size is reducing. So, now it is no longer able to accommodate so many C314 attached with it. So, therefore, some of them are getting released, and which gives you fluorescence. Okay. So, it is a nice application of this fluorescence spectroscopy. Okay, fluorescence spectroscopy, that you can employ fluorescence technique in detecting ions. So, therefore, this gives you an idea. This gives you an idea of this application of this nanomaterial in identifying, or maybe in just knowing which ion is there in your mixture, okay, whether it is sulfide or cyanide. Suppose you are having a sample, maybe containing sulfide or maybe containing cyanide or maybe containing sulfide and cyanide both, and you are asked to examine, okay, whether sulfide is there or not. Somebody is telling you that, okay, it is suspected that sulfide ions are there in a given sample. Then what could be the process? Okay. Now, before that I should tell you one thing, that lowest detection limit is 60 parts per billion for both sulfide and cyanide. So, therefore, if your sample contains this or that sulfide or cyanide of the order of 60 parts per billion or more, then this method may be very fruitful. Okay. So, in that case, what you do, if you are asked to examine this, then you just follow the protocol and then prepare your nanoparticle by means of this photochemical route, okay, and then you employ, just maintaining the conditions, you employ that nanoparticle along with C314, and then put your unknown sample, okay, put your unknown sample first, that whether your fluorescence is turned on or not. Okay. So, if there is sulfide or if there is cyanide or both together, okay, then and they are either 60 ppb or it is more than 60 ppb, then it is probable that it will happen that this fluorescence will be turned on. So, that means you are sure that, okay, impurity or suspected impurities are there. Okay, suspected impurities are there means you can now, okay, examine vividly whether this impurity, suspected impurity or suspected ions are there. So, therefore, now it is the question whether sulfide is there or cyanide is there. Then you use this technique, that in presence of Cu plus and plus your sample, if you are getting this one, then you are sure that it is sulfide. In presence of lead 2 plus and cyanide, if you are getting this, then you are sure that you are sure that cyanide is there. So, if both these steps, okay, both of these two steps, if these two respond, then you are sure that both sulfide and cyanides are present. But if only one is responding, then either this one or that one is present. Okay. So, you see that how this fluorescence technique, turn on assay technique, along with this nanomaterial is helpful in detecting various ions. There may be other applications as well, like detection of maybe glucose, detection of some other molecules, small molecules or larger molecule, that is possible. So, in that case you need to devise a material which is specific to that particular molecule, or maybe a material which is specific to some particular thing or particular substance, depending on the condition. Like here you have a material, you have devised a material which has got a dual property, okay, like it has the capability of sensing cyanide and capability of sensing sulfide as well. So therefore in this way, if you can design a specific material, okay, if you can design a specific material, then it can be nicely employed to do this sensing business. Okay. So, so in this way there may be other examples as well. If you look into literature, you will be finding that there is a tremendous volume of work that is that are being published in literature, which talks about sensing of different materials, and of these procedures, among these procedures, I mean the procedures by which this sensing is done, is the fluorimetric method. Okay, like what I discussed over here is the fluorescence turn-on assay. Okay, so in this way, this fluorescence technique, I just gave you one example. Okay, you can find many examples. Okay, many examples of such sensing things. Okay, so therefore nanoparticles coupled with a sensitive fluorescence technique can be very helpful. In doing many applications, maybe one of which is your sensing. Maybe some of them have some improved physical properties. Maybe some of them have like improved or higher conducting property, or maybe better optical property. Okay, so those can be employed. So since this set of lecture is mainly related to fluorescence, so I just gave you the idea of this fluorescence sensing part. I mean sensing involving fluorescence spectroscopy. Other things are available in literature, you will be finding. So so in this particular lecture, what we have learnt is, we just have a very brief overview of what are nanoparticles and how these are synthesized, okay, and maybe after synthesis how this can be used in some applications. Like here today I just talked about this fluorescence turn-on assay. Okay, so in the I mean that's all for today's lecture. So in the next lecture we are going to take up another aspect of this nanomaterial, is nanocrystal, where actually this photoluminescence of nanomaterials will be used, will be employed for different, maybe that can be employed for different sensing applications, maybe some other materials applications. So that we are going to take up in the next lecture. So till then, have good time. Thank you.